I'm Becca, and this is my Constant Velocity Lab. So, a brief introduction. The purpose of this lab was to construct a computational model based on Newton's second law, also known as the momentum principle, that accurately describes the constant velocity of a tennis ball rolling on wooden floor. Some models and principles that we'll touch on include Newton's second law, which states that if the net force exerted on a system by its surroundings is zero, then the change in momentum should also be zero. We'll also touch on a variation of the position update formula, and everything will connect back to Newton's first law of inertia. Preview of results. The slight difference between the observed and predicted position versus time graphs are due to unaccounted net forces acting on the tennis ball in the direction opposite of motion. And some examples of these unaccounted net forces could be friction or air resistance. The system in this case would be the tennis ball, and the surroundings would be the wooden floor the tennis ball is rolling on and the earth as a whole. Some pre-lab information. For initial conditions, I just wanted to include that the mass of the tennis ball is 0.25 kilograms. The beginning position is the zero vector. The ball is moving right after a push to begin its motion, so it's moving in the positive x direction, and it's moving with an initial velocity of 2.45 meters per second. Some assumptions are that friction and air resistance are negligible, the wooden floor is flat, meaning there are no bumps, and the push to begin motion is not included in the net force calculation. Experiment details. The tennis ball begins its recorded motion at the zero vector and ends its recorded motion at the vector shown. The ball started at the origin and moved in the positive x direction, which is to the right in this case, as the arrow is depicting. Here's a video of the experiment. Some details of my code. I put 0.25 kilograms in for the estimated mass to account for that. I changed the initial velocity vector from the zero vector to the vector shown. I changed the time while loop to run until 2.29 seconds, and I left the net force vector at 0 to assume no net force. I also changed the time step from 0.01 seconds to 0.05 seconds, and I changed the position update formula to have velocity vector at a constant value. And that is a link to my code. So comparing models. So I put the observed position and predicted position on this graph versus time on top of each other so you could see how the relationship between them and how they relate to each other. So the predicted position is obviously a constant velocity, a constant slope, a straight line, and then you can see how the observed position alternates between being above that line, below that line. It's sometimes steeper than that line, sometimes it's not, and the inconsistencies and why these two lines are not right on top of each other is because of underlying forces that we could not possibly account for, and possible errors, and we'll go into that later, and why these two lines are not the exact same. So discussion of results. The predicted computational model follows the actual observed motion of the ball fairly well using our calculated average velocity. However, there is a slight difference, and it is due to how the observed motion does not maintain its initial velocity over the entire time interval. The momentum principle states that the change in momentum of a system is equal to the product of the net force acting on the system and the duration of time that interaction is occurring. It reflects that if no net force is exerted on the system, then momentum should remain constant. Because the mass of the ball is constant, momentum being constant and the lack of net force being exerted on the system would mean there's no change in velocity. However, we only accounted for gravity and the normal force on the system, so the forces we did not account for, such as friction or air resistance, must have had an impact on the system. Air. Most likely explanation for the slight deviation from the constant velocity is the presence of kinetic friction. Kinetic friction opposes motion, and we assumed there was no friction, but our observed position differed from our predicted position, concluding there was non-constant velocity. So we do believe kinetic friction was present at some point. So what if the axes were interchanged? So we measured the ball moving in the positive x direction, which was to the right, but if the ball were to move in the negative x direction to the left, the graph would be flipped 180 degrees. The slopes of the graph were originally positive, but they would change to negative if we were to flip the direction. So as you could see in the graph earlier, the lines were going to the right and up, but if we were to change them, they'd be going to the right and down. The distance traveled will not change, but the appearance of the graph will. So for some further consideration, gravity and the normal force cancel out in the y dimension. The net force considers all surroundings, including Earth, and it is not possible to identify all the forces that add up to zero. Some conclusions. The observed motion of an object can be predicted well by computational methods. By the momentum principle, any net force from friction will cause a slight change in momentum and a deviation from the computational model. A movement free of friction is highly unreasonable. Regular motion will not adhere to a computational method devoid of a net force.